So we have air enters a turbojet engine at 26 kPa and 230 Kelvin and an inlet velocity of 220 meters per second. The air mass flow rate is 25 kilograms per second. That piece of information, you just tuck it to the side because it's not needed until part B, and there's a lot of work to get to part A finished. The pressure ratio across the compressor is 11. Does that mean the pressure ratio across the turbine stages are 11? Not at all. And it's going to be less. It's going to take it down just enough so you have a lot of pressure to push it through the nozzle to really get that high exit speed. Okay? The turbine inlet temperature is 1400, metallurgical considerations. The work developed by the turbine equals the compressor work input. That's kind of stating the obvious, but that's just emphasizing this is a turbojet. We'll later talk about a turbofan and a turboprop. But for a turbojet, no external shaft power developed or produced. The diffuser, the front part, and the nozzle, the end part, are isentropic. Or you could get some isentropic efficiencies for those, but it's isentropic. The isentropic efficiency for the compressor is 85, for the turbine is 90%. Added complexity. There's no pressure drop for flow through the combustor, so that's a standard assumption. It operates at steady state. Kinetic energy is negligible except at the inlet and at the exit, because the kinetic energy, Ke, is that 1/2 V squared. The specific kinetic energy, it is. And so we're trying to get the velocity at the exit to be as high as possible. Probably don't neglect the kinetic energy at the exit. Okay. And similarly, they give you 220 meters per second. So it has some inlet kinetic energy coming into the engine. So what is the velocity at the nozzle exit? A lot of work to make that calculation. The best thing to do is go ahead and sketch and then make a table of properties, especially the first time through. So let's I'm going to kind of put it as a box. A diffuser, followed by compressor, followed by combustor, followed by turbine, followed by nozzle. True? Okay. And sometimes that diffuser is optional, so it's often the flow here. Let me see if I could draw it this way, going through. A lot of times you like to start with state 1 here, and then 2, then 3, then 4, and then 5, and being consistent with the book, label that state A, not state 0, not state 1, but state A, just to be consistent with the textbook. True? So we are given the information about the pressure at A, right here. Pressure at A is 26 kilopascal. The temperature at A is 230 Kelvin. And the speed at A is 220 meters per second. What I do is make a nice little table. And so we'll have state, okay, and then pressure in kilopascal, temperature in Kelvin. And this velocity column is going to be 0 for most states, but since the first and the last state are what's important, put it in there. And then specific kinetic energy, I like to put that as a separate column, kilojoules per kilogram. And then the enthalpy, kilojoules per kilogram. And then because we're going to be doing pressure changes and isentropic compression, put piece of R for that column in the air table to help us do isentropic processes from state. We'll start state A, so we come in at 26, 230, 220. So we can calculate that kinetic energy. We already know the kinetic energy equation. That's 1/2 V squared. But don't forget a unit conversion factor that 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. Do you remember that unit conversion? That's right. So that when we calculate that kinetic energy, it's 24.2 kilojoules per kilogram. And then we know that enthalpy is a function of temperature. At that temperature, it's 230.02. We're going to go from state A to state 1. When we go from state A to state 1, what do we know about that process through the diffuser? Isentropic, S is equal to a constant. So that's why we'll go ahead and get the P sub R at state A. P sub R is only a function of the temperature. P sub R is 0.548. It's good to 3 digits, maybe there's more. And now I have isotropic compression through the diffuser. I want to calculate, do an energy balance first. Okay? If you do an energy balance first, what is the enthalpy at 1? Is that equal to the enthalpy at A plus the kinetic energy at A? From an energy balance. So we take this enthalpy and that enthalpy. Now we know the enthalpy at 1, it's 254.22. All right, knowing that enthalpy, can I get the temperature at 1? Yeah, enthalpy is only a function of temperature. So if I know the enthalpy, I can get the temperature. Likewise, if I know the temperature, I can get the enthalpy. It's an ideal gas. We're using air as an ideal gas and using the air tables. So we can get the temperature there. If we wanted it, we don't really need it, 254.2, but conceptually it's like, okay, I get back to temperature. Because now, can't I get P sub R? Really, I could get P sub R as a function of H, or P sub R as a function of T, either one. But I get P sub R, and it's 0.778. What does that tell me? Yeah, it gives me the pressure ratio across the diffuser. So the equation that I have is that P sub 1, is that the equal to P sub A? Is P sub 1 equal to P sub A? No. It's higher or lower? Pressure 1 higher than A or lower than A? Higher. True? It slows it down, builds up pressure. And when later we're going to talk about supersonic flow, but this is all subsonic. You've solved enough problems with it. Hopefully that makes sense, that in a diffuser it slows down and builds pressure. The area increases as it goes through the device. Okay, so this is P sub R1 divided by P sub RA for isentropic compression. So it's 0.778 divided by 0.548. And so we calculate P1, it's PA of 26 kilopascal times that. So it picks it up to 36.9 kilopascal. So that's the pressure, 36.9 kilopascal at the beginning of the compressor. First of all, let me back up a little bit. 26 kilopascal, high pressure, low pressure. Tell me a little bit about that. It's low. Why would we have low pressure? This is flying at high altitude. Right? That's the application. It's flying at high altitude. So it's not atmospheric pressure at sea level. Okay. Now we go through the compressor, state 2, but they give us the isentropic efficiency for the compressor, so I suspect I'm going to need 2S and then 2. I'll have to do it in 2 stages, right? So they tell me that the outlet to the compressor, it has a pressure ratio of 11. The pressure ratio across the compressor is 11. So what is PR2S? Isn't that 11 times 0.77? So this is 8.553. See how we did that? So I have the pressure ratio for the isentropic state 2S, or isotropic compression through the compressor. Okay, that allows me to get H2S, and then H2S is 505.39. So I calculate the work. I'm going to just write it over here. I'm going to have to erase it. The work, compressor isentropic. Isn't that the difference in the enthalpies? Is that 505.39 minus 254.22? So isn't that work 251.2 kilojoules per kilogram? So that's the minimum work to achieve that pressure ratio. But we have isentropic efficiency of 85%, so the work compressor actual is work compressor isentropic. Multiply or divide by 85%. You're good. And so we actually have to supply more, 295.5 kilojoules per kilogram. So we add that to 254, and we find out it's 549.71 kilojoules per kilogram. So that's our 2 steps going through the compressor. True? If you wanted to, could you get to temperature at state 2 actual? Sure, it's a function of enthalpy only. Interpolate in table A22. How about the pressure at state 2? You're given the pressure ratio 11. Multiply 36.9 by 11, you get 406.0. So 406 kilopascal. The real kicker is we want those enthalpies. It's nice to look at the temperatures and pressures, but we really need to keep track of those enthalpies. True? I'm going to go ahead and try and erase this work of the compressor and isentropic work of the compressor. Unless you have a question, I'm going to erase it right now, okay? So that I can keep on one page without flipping and going to another page. Now we go through what do we go through? The combustor. And we come out at state 3 at a given temperature, and that temperature is 1400 Kelvin. Let me just fill in temperature. No, I never did calculate 2 actual temperatures, so I just left it blank. I never did calculate it. All right, and we know this pressure is 406, and we look up the enthalpy as a function of temperature. It's 1515.4. And we're ready to go across the turbine, and we're going to have 4S and 4. So I need to get PR for state 3. That's 450.5. And now I will figure out how to make this calculation. I don't know the pressure ratio across the turbine. It's just enough to allow the turbine to do the work to supply the power to the compressor. That's exactly the key observation. You have to make that observation. And the first time you do it, you struggle and you say, how do I solve for this? Because I'm used to having the same pressure ratio, but you don't have the pressure ratio across the turbine. What you are given is that the work that the turbine actually produces is the work that the compressor actually needs. And so you know you're coming in with this enthalpy, and you're going to skip enthalpy 4S, and you're going to get enthalpy 4 actual right now. That's a little slippery or a little tricky. So you actually calculate 1219.93 because you subtract off 295.5 kilojoules per kilogram off of enthalpy 3. Right? This was 295.5 kilojoules per kilogram. Thumbs up if you agree. Do you have that down on your paper? Okay. Now that I have the enthalpy at state 4 actual, okay, how do I get the pressure ratio? That's a little tricky, but can you do me this? Can we now calculate H4 isentropic? Okay. Is it going to be higher or lower than 1219? It's going to be higher, it's going to be lower. The work of the turbine isentropic is that going to be the work turbine actual multiplied by the isentropic efficiency of the turbine, or divided by the isentropic efficiency of the turbine? Which? So it's going to be this. You agree? And that isentropic efficiency is 90% for the turbine. And so we find that the work, if it had been isentropic, would have been able to produce 328.3 kilojoules per kilogram. The assumption is these have the same pressures. 4S and 4 have the same pressures. Okay, so now that I know that this is not 1219, but it's 1187.1, can I use that to get PR 4S? Yeah, you just interpolate in the table knowing enthalpy at state 4S to get PR 4S. When you do that, you get that this is 181.3. That gives us the ratio of PRs, which is equal to the ratio of the actual Ps. Just like here, we did this. Okay, we're going to do it again for the turbine. So we get PR3 divided by PR4 is equal to P3 divided by P4. True? Well, it's PR4S. This is an assumption that they're the same pressure, just like these are the same pressures. So we find that the actual pressure ratio is a whopping, let me see how this, it's 2.48 instead of 11. So think about it. You could go from, you went from 1 to 11, now you're up at 11, you're going to come back down, but you don't need to go all the way down, you just need to come down like 2.48. That means you got a lot of pressure left to push it through the nozzle to get it high exit speed. So when we calculate this pressure at state 4S, which is the same pressure at state 4, it's 163.4. They're the same, so we calculated it for 4S right there. Okay, that was a big step in the process, wasn't it? Ready to continue? Can I erase this right here? Let me erase it. Now we're ready to go from 4 to 5, and 5 is 5S. There's no difference between, because it is isentropic. Through there? So how am I going to go from 4 to 5 through the nozzle? Well, we want this to come out at very high speed, V5. That's what we're interested in, the exit speed. That's what we're trying to solve for, V5. Now you get the PR at 4, which is 200.6, because you're now isentropically expanding from 4 axial to 5. True? Through that nozzle. So yes, that's key right there to get that new PR at state 4. Okay, how am I going to use that? So P5 is back all the way to 26 kilopascal. A student may think that it's back to 36.9 kilopascal, but it's not. It's back to the ambient outside pressure where that engine's at, which is 26 kilopascal. So knowing that actual pressure at 5 and this PR here, we can get PR at 5 because you've got to go from this pressure to that pressure. So should I write that equation down? I have to scoot a little more. But it's just like this equation, just like this equation. Let me write it down. So what we have is we have that the pressure at 5 compared to the pressure at 4, both of those we know, is PR at 5 compared to PR at 4. So known, we calculate PR at 5. When we calculate PR at 5, we come up with 31.91. Why? Well, we have to get the enthalpy at 5. So it goes to 734.08. Well, that doesn't make sense. You expanded it through a nozzle, and the enthalpy dropped from 12, almost 20, to 734. Where did all that energy go? Went to kinetic energy. Exactly right. So now, from the energy balance, you have the enthalpy at 5 plus the specific kinetic energy at 5 is equal to the enthalpy at 4. That difference is the kinetic energy at 5. And when we calculate that kinetic energy at 5, it's a whopping 485.85 kilojoules. 485.5 kilojoules per kilogram. That is 1/2 V5 squared. Don't forget the factor of 1,000 on your unit conversion. And now you can compute that this is 986 meters per second. So it came into the engine at 220, it comes out of the engine at 986 meters per second. No change in the mass flow rate. The analysis has no added fuel mass flow rate. It's the same mass flow rate. True? So that's our answer here for part A. 986 meters per second. The forward thrust, how do we calculate that forward thrust? Well, it was the mass flow rate times V2 minus V1, which is 25 kilograms per second, times 986 minus 220 meters per second. Okay, what is a kilogram meter per second squared? A newton. So a newton is a kilogram meter per second squared, and you get newtons for the thrust. Okay? So that's the answer to part B.